Hello everybody, in this lecture we will be solving 1997 IMO problem number 6. Here is a view of this problem. For each positive integer n, let f of n denote the number of ways of representing n as a sum of powers of 2 with non-negative integer exponents. Representations which differ only in the ordering of their summands are considered to be the same. We're given an example for the case 4. It looks like 4 can be represented in 4 different ways, namely as 2 squared, or as 2 to the 1 plus 2 to the 1, or 2 to the 1 plus 2 to the 0 plus 2 to the 0, or 2 to the 0 plus 2 to the 0 plus 2 to the 0 plus 2 to the 0. Notice here that if like 2 plus 1 plus 1 is the same as 1 plus 2 plus 1 or 1 plus 1 plus 2, right? So we are really considering the number of partitions, in a sense, partitions into powers of 2 where ordering doesn't matter. Okay, so we would like to show, find lower and upper bounds for the following expression. So let's start with the upper bound first, and then I will focus on the lower bound. So let me first show that, let's call it the first part, the upper bound for f of 2 to the n. Okay, so first let me try to recursively describe the function f. Consider a representation of an odd integer. First, an odd integer like this in the form 2k plus 1, and when I represent it as a sum of powers of 2, obviously it will definitely have a 2 to the power 0 in it because of that 1 here. So what I can do is, if I remove the 2 to the 0 from that expression, what I will get is an expression for an expression for the number 2k, right? So removing 1 from this we will be left with 2k. But notice that I can this procedure is reversible as well. So if I have an even integer, I can simply add 1 to it, add 2 to the 0 to it, and I will get a 2k plus a representation for the number 2k plus 1. So as a result, I have my recursion, right? So for the expression 2k plus 1, we got a bijection here. So f of 2k plus 1 is simply equal to f of 2k. That's the first formula. Let's call it number 1 here. Secondly, let's start with an even integer now, like 2k. So if this expression has a 1 in it, so there are two choices, right? So it's possible to partition it where it has a 1 in it, has 2 to the 0 in it, 2 to the 0, versus does not have 2 to the 0. So some partitions will include 2 to the 0, some won't. So for those who include 2 to the 0, if you simply remove one of these ones, and at least we should have an even number of ones, but if you remove at least one of them, we will be left with 2k plus 1, a representation for a sum of 2k plus 1, and we already know a representation for it. So f of 2k plus 1 will count this. F of 2k minus 1, sorry for that. When I remove 1, I will get 2k minus 1 such representations, right? And if it doesn't include a 1, then I can be really smart and I can do the following. It means that all the numbers in the partition are powers. So if it doesn't have a 2 to the 0, it means that all the summands are 2 to the 1, 2 squared, and so on. But all of these are even. So what I can do in this case, I can divide the whole thing by 2. I can scale it down by 2. In that case, I claim there's a bijection between this and dividing by 2. Now the numbers will sum to k, and the number of such representations is now f of k. So therefore, if it includes a 1, at least remove one of the ones, you would have a representation, that many representations, right? So f of 2k minus 1 such representations, versus if it doesn't have a 1 in it, you would get this many, and that would be pretty much the count for f of 2k. Let's write that down as well. So therefore we have f of 2k is equal to f of 2k minus 1 plus f of k, and that's my second relation. And these relations will hold for k equals 0, 1, 2, and we can also by convention assume that there's only one way to come up with f of 0, right? And in this case, so that's how we can establish that this formula also works for k equals 0. So now it's we can combine these two results to come up with some really nice recursive forms. While combining Formula 1 and Formula 2, we just realized that this is an odd number, and the number of representations for an odd number. So, and this is given by this formula. So therefore, the formula here will become, if I combine 1 and 2, I'll get f of 2k is equal to f of 2k minus 2 plus f of k. And now this holds for, at least k should be, k equals from 1 to, like this. So what I can do is, I can, let's write it with blue again. So let's now do the following trick. So fix an r greater than or equal to 1, and we can add up all these inequalities under each other. So therefore we would get, so starting with k equals 1, we would get f of 2 is equal to f of 0 plus f of 1, and then so this one is r equals 1, r equals 2, we'll get f of 4 is equal to f of 2 plus f of 2, then r equals 3, f of 6 is equal to f of 4 plus f of 3, and so on, right? So let me keep that formula here, all the way to r. Okay, so the general term, f of 2r, or I can do it first r minus 1, I'll get f of 2r minus 2 is equal to f of 2r minus 4 plus f of r minus 1. Finally, for r, f of 2r is equal to f of 2r minus 2 plus f of r. Now I can just add these expressions, and we would have quite a few terms cancel out actually. So all these terms will cancel out, and we would get the following final recursive form. F of 2r is equal to, on the left hand side, on the right hand side we would have f of r, the largest of these terms, plus f of r minus 1, all the way up to f of 2 and f of 1 and f of 0. Now this recursion, I ordered the terms on the right side from the largest to the smallest because I know the function f is non-decreasing. So I can do even more. Notice that I can, for instance, notice that whenever r is greater than or equal to 2, f of r would be, so for instance, f of 2 is simply equal to 2, because 2 can be written as 2 or versus 1 plus 1. So there are two ways to express it, and so on. F of 3 will be even, so this is a non-decreasing function. So f of 3, for instance, would be, you can write it as 2 plus 1, or you can write it as 1 plus 1 plus 1, so it's at least 2. F of 4 will be even higher, right? So it would be 4. Oh, we already did f of 4 actually. So it's a non-decreasing function. As a result, I will do the following trick. I claim this expression. So if you bundle together all these, actually I can leave these to the last two on their own. So each of these is equal to 1, by the way. So this is equal. So we have, I know that this expression here on the right side is greater than or equal to, if I replace each of these terms by f of r, knowing that our function is non-decreasing, we have r minus 1 terms here, times f of r plus 2, and this is simply this is simply again less than or equal to r minus 1 times f of r. Again, 2 is less than or equal to, so this thing, sorry, it should be greater than equal to 2. F of r is greater than or equal to 2. So therefore, this is less than or equal to plus f of r, which is simply r times f of r. So therefore, we know, so this implies, therefore, f of 2r is less than or equal to r times f of r. And that holds for all r greater than or equal to 2. Now I can set r is equal to, well, you can recursively apply it, right? So let me write it in the following manner. So let's start with f of 2 to the n. F of 2 to the n can be written as f of 2 times 2 to the n minus 1. But then using this new form, inequality, this would be less than or equal to 2 times f of so f of 2 to the n minus 1, but then I can repeatedly do the same procedure. So that's 2 times f of 2 times 2 to the n minus 2, and then moving out the 2, we will get 4 times f of 2 to the n minus 2, which can be further split into 4 f of 2 times 2 to the n minus 3, and so on. And we know how the thing will continue from here. So repeating this procedure many times, we would come up with the following expression. We would come up with 2 to the n minus 1 times 2 to the n minus 2 all the way up to 2 squared times 2 to the 1 times f of 2. And finally, that would simply be equal to f of 2, recall, is equal to 2. So this one is equal to 2. So we would get the sum of positive integers from 1 to n minus 1. So this would be just n minus 1 times n over 2. So therefore, we would get 2 to the power n times n minus 1 all over 2 times 2, which is basically strictly less than 2 to the power. We would get n squared minus n over 2 plus 1. So therefore, this is definitely strictly less than 2 to the power n squared over 2. And this proves the upper bound as we wanted. So now how about a lower bound? So this lower bound that we are interested in. So we will keep making use of these 3 formulas that we have just derived. Actually, let me remind them. So for the lower bound, now recall our formulas, namely f of 2k plus 1. The number of representations for an odd number is simply equal to this. Then we established f of 2k, which is simply f of 2k minus 1 without a 1. With a 1 plus f of k, those representations of 2k without using the numbers ones. And finally, the recursion with lots of terms, f of 2r is equal to f of r plus f of r minus 1, and so on. F of 2 plus f of 1 plus f of 0. We established these 3 already. So for the lower bound, I start again with this one, consider f of 16q, where q is greater than or equal to 1. That's simply equal to, using this one, it would be f of 8q plus f of 8q minus 1, and so on, all the way up to f of 1 plus f of 0. But I can simply remove some terms from the right hand side to make the right hand side smaller. So therefore, this would be strictly greater than f of 8q plus f of 8q minus 1 all the way up to f of 6q. I'll just stop at 6q. And that one, in its turn, is strictly greater than, we do have 2q plus 1 terms here, 2q plus 1 terms. And the least of these terms is f of 6q. So therefore, this would be definitely strictly greater than 2q times f of 6q, the smallest one. In fact, this is a much weaker condition here. And then this is actually equal to 2 times q times, I can replace now 6q with, again employing this formula, f of 3q plus all the way up to f of 1 and f of 0 here. And then I can use similar tricks repeatedly. I have 2q, and I can just remove some terms from the right hand side. So namely, I can start from 3q all the way up to 2q, and then there's at least q terms here, q plus 1 to be exact. So this is 2q times q times, and not equal to, greater than, strictly greater than 2q times q times f of the least of them is 2q here. And now it's time to plug in for q in this expression, in this final expression. If we plug in 2 to the n minus 1, we will get f of 2 to the 4th power times 2 to the n minus 1 would give us 2 to the n plus 3rd power is strictly greater than, we have 2q squared times f of 2 times this would be f of 2 to the n. And now we have this expression for n is equal 1 to all the way, and now, making use of this, knowing this is true, I will attempt to prove the desired result, the lower bound. So this lower bound, this one, using induction actually. So 2 to the power n squared over 4. So 2 to the power n squared over 4 is strictly less than f of 2 to the n. Okay, so we want to show prove this by induction. Use induction to prove it. Use induction show. So we need to show this, and for that we will be using induction to come up with this our final result. So let us skip the base case for now. So the base case is a little bit problematic, but let's go to the induction step. So by the induction step, let's assume that our relationship, namely induction step. So let's assume that this relationship 2 to the n, f of 2 to the n, is strictly greater than n squared over 4 for some certain n, and then we would get, okay, so let's start with f of 2 to the n plus 3, our expression here that we already have some information, 2 to the n plus 3. This is strictly greater than, oh boy, okay, so I did another very silly mistake, sorry for that. So here we had this expression being strictly greater than this one, and we said that we would replace q with 2 to the n minus 1. I did in fact replace it inside the f, but I forgot to replace it here, so I'll just erase it. So replace the 2 times q squared. So q squared would be 2 to the power n minus 1, the power multiplied by 2, so that would be 2 times 2 to the 2n minus 2, but then multiplying by 1, that would be minus 1 simply. So 2 to the power 2n minus 1. So sorry for that. So we have already proven this. Knowing this, we would like to show this result. Okay, so f of 2 to the n plus 3 is strictly greater than this expression, which we already know. Okay, so that's nice. And by this induction step, we assume this holds, so let's just replace this with, so 2 to the 2n minus 1 with this expression here, 2 to the n squared over 4, which is simply 2 to the n squared plus 8n minus 4 all divided by 4. Right, and what we actually need on the right side is 2 to the power, so we would like to show that, we would like to actually show that this is strictly greater than 2 to the power, and replacing n with n plus 3, I would get 2 to the power n plus 3 squared over 4. So namely what this means is, this implies, so therefore I would like to show equivalently that n squared plus 8n minus 4 is strictly greater than n plus 3 squared, which is just n squared plus 6n plus 9. The n squares will cancel out. We would have 2n is strictly greater than what? 13, which implies n is greater than 6.5. So therefore this would hold true for n equals 7 and above, right? So that's great. So all that we need to finish the proof then is to verify that the claim also holds, and because n here was so we had an expression for n plus 3 here, so all we need is that to show that this thing would also hold for so this would be 2 to the 9 when I plug in 7, sorry, 2 to the 10. So anything f of 2 to the 10, anything above works. So therefore I need to show for, this is kind of like our base case, show it works for f of 2 to the n where n is less than or equal to 9. So we need to show that this holds. So I need to one by one show that each one of them satisfy this. We have 9 of these expressions. It will be a little bit time consuming, right? Not too hard, but time consuming. So that's why it might be well, yeah. So I mean, at this stage you guys can one by one show for each and every single one of them. So starting by plugging in 1 here, f of 2 is f of 2 strictly greater than the 4th root of 2, of course. Then you would go to 2, is f of 4 less than 2, of course, because f of 4 is, sorry, greater than, f of 4 is equal to 4, and so on. A more efficient way would be to right, so what we can do is, yeah, so we can do a couple of things. We can calculate, let's start with f of 8. We can calculate f of 8 using our recursion formulas, right? And if you use them carefully, our three recursion formulas here, so f of 8 would be equal to, so I can use first this one and then I can plug them in further recursively, and you would get f of 8 would come out as 10, okay? And in a similar way, f of 16, which is just f of 2 times 8, which is you already know, so you can do the algebra as well. And for this one, I think you come out with 36, and finally f of 32 would give you 202. But then we can make use of yeah, so our long recursion in the following way. So we would just observe that f of 4j is equal to, and remember our third recursion, f of 2j plus f of 2j minus 1, all the way up to, so here I will draw the following trick. I will stop at f of j here, f of j plus 1 I should say, f of j plus 1 plus f of j, and so on, all the way to f of 1 plus f of 0, and I will split it into two pieces, this piece and the remaining piece. So this implies that this is strictly greater than, so for these expressions we have j of them, and each one is greater than f of j because our function f is non-decreasing, so this is strictly greater than j times f of j plus, and then this portion here is simply f of 2j plus f of 2j. So here we can set for j equals 16, so we would get f of 4 times 16, which is just f of 64, is strictly greater than, so setting up 16, so we would get 16 times f of 16, right, plus f of 32, but we already calculated these, so this is simply 16 times 36 plus f of 32 was 202, and that comes out as, if I'm not mistaken, let me see, yeah, it would come out as 778, which is definitely greater than 2 to the power 9, which is 512, right? 512. So therefore, well, and in a similar way, you would get that f of 128 is strictly greater than, I think this one comes out as 7,242 if you apply a similar trick, which is again strictly greater than 2 to the power 10 is 1024, 2 to the power 11 is, and then 2 to the power 12 is 4,000. So this is definitely strictly greater than 2 to the power 12, which is actually, it might be a little bit more greater than that. Right. Actually, does it make it, we need to show this, right? So I need to be careful here. So when n is equal to, okay, so here we got 64. 64 worked really nicely because 64 is simply 2 to the 6. So 6 squared is 36 over 4, 9. So that one works. So n equals 6 works. So here we showed n equals 6 works. Here n equals 7. N equals 7. I should have gotten 49 over 4, which is 12.25. So I need a little bit better than this. So I need to be more careful. I need 12.25 at least. So yeah, so this is greater than 2 to the power 12, which is 4,000 something 96 times is it greater than the square root? Square root of 2? Square root of 2, let's write it as 0.5. Square root of 2 is, yeah, it is. Because square root of 2 is 1.4. If you multiply 4,000 with 1.4, it will still be in the range of 6,000 or so. So this is definitely greater than, when you add them, 12.5, definitely greater than 2 raised to the power 12.25. And in a similar way, it's you can also find the same expressions for 256 and f of 512 as well. I think 256 comes out as 2 to the 16 as we wanted, and then this one 2 to the 20.25 as desired as well. So this is for n is equal to 8 and n is equal to 9. We did accomplish the smaller ones earlier. N is equal to 3 here, n is equal to 4, and n is equal to 5 as well. Okay, so therefore we have just shown that the desired result holds for all the numbers n even less than 9, less than or equal to 9, by using an induction argument, and that shows that the lower estimate also holds, the lower bound, sorry for that, the lower bound is also true, and we are done.